Hello and welcome to yet another lecture on basic electrical engineering, paper code ES-EE101. Myself Prathita Roy, Assistant Professor of Dr. Sudhir Chandra Institute of Technology and Sports Complex, Department of Electrical Engineering. Today, my topic is magnetic materials and pH characteristics. So lesson objective. After end of this topic, student will able to understand the concept of magnetic materials and pH characteristics. So we are starting with magnetic materials. So content, introduction, terms connected with magnetic materials, classification with properties and applications. So we start with introduction. Magnetic materials are those materials in which a state of magnetization can be induced. So magnetization or magnetization magnetism occurs when negative and positive particles in an object line up in a specific manner, causing an attraction or repulsion with nearby particles. This is the general conception of magnetism. Such materials, when magnetized, create a magnetic field in the surrounding space. Terms connected with magnetic materials: magnetic force, magnetic flux density, magnetic field strength, relative permeability, absolute permeability, remanence, retentivity, Curie temperature, hysteresis loop, and losses. So classification. The materials are classified as a ferromagnetic, paramagnetic, diamagnetic, magnetically soft material, magnetically hard material. Now ferromagnetic material, a type of material that is highly attracted to magnets and can become permanently magnetized, is called as ferromagnetic material. The relative permeability is much greater than unity and are dependent on the field strength. These have high susceptibility, high susceptibility, These have high susceptibility. So this is the general property of ferromagnetic material. The relative permeability is much greater than unity and dependent on the field strength, and the susceptibility is high. Now, some example of ferromagnetic material are FeCO, Ni, Cr, Mn are such materials. So this is the alignment of ferromagnetic materials, or in other words, it is said that the alignment of moments resulting in large net magnetization in the ferromagnetic material, and that it is clearly seen that the alignment are generally known as parallel alignment of moments in ferromagnetic material, and this is the ferromagnetism. The alignment are shown is the parallel alignment of moments in ferromagnetic material. Next one is paramagnetic. It is a substance or body which were weakly attracted by the poles of a magnet. The attraction is weak by the poles of a magnet, but not retaining any permanent magnetization, or the magnetism is known as paramagnetic material. These have relative permeability slightly greater than unity and are magnetized slightly. They attract the lines of forces weakly. So Al, Pt, CaO2 are such materials, and this is the general overview of paramagnetism. And this is the alignment of moments, or the resulting moments in paramagnetic material is shown here. Now diamagnetic. This is a substance which create a magnetic field in opposite to an externally applied field. A magnetic field which is generated in opposite to an externally applied field. Susceptibility is negative. These have relative permeability slightly less than unity. They ripple the lines of forces slightly. This is generally known as diamagnetic material. Some examples of diamagnetic materials are bismuth silver, copper, and hydrogen. And this is a general overview of diamagnetism. General overview of diamagnetism. Now, magnetically soft material. The characteristics of magnetically soft materials are They have high permeability. The magnetic energy stored is not high. They have negligible corrosive force. They have low remanence. Hysteresis loop is narrow. Example: pure or ingot iron, cast iron, carbon steel, manganese, and nickel steel are the example of magnetically soft material. Magnetically hard material characteristics are: they possess high value of pH product, high retentivity, high corrosivity, strong magnetic reluctance. Hysteresis loop is more rectangular in shape. Some examples are tungsten steel, cobalt steel, chromium steel, etc. are some example of magnetically hard materials. Now application. Ferromagnetic materials are used in magnetic recording devices such as for cassette tapes, floppy disks for computers, and the magnetic stripe on the back of credit cards. Magnetic materials are used for magnetic levitation, where an object will be made to float in or above a strong magnet. Magnetic soft materials are used in making electromagnets, and these electromagnets are used in telephone receiver, bells, loudspeakers, etc. Magnetic hard materials are used in making permanent magnets. So we have already discussed about the magnetic materials along with their characteristics and different types of magnetic materials and along with their application. Now we will discuss about we have seen that the hysteresis graph, hysteresis curve, in other words, of different magnetic materials. So now we will discuss about the pH characteristics of magnetic materials or the pH characteristics. So first is the what is pH curve. A pH curve plots changes in magnetic circuit's flux density to magnetic field strength. As the magnetic field strength is gradually increased or decreased, so it is generally the plots that changes in magnetic circuit flux density to magnetic field strength. As the magnetic field strength is gradually increased or decreased. The resulting shape indicates how the flux density increase or decrease due to the gradual alignment of the magnetic domains atom that behave like tiny magnets within the magnetic circuit material. So the resulting shape that indicates how the flux density increase or decrease due to the gradual alignment of magnetic domains within the magnetic circuit material. So this is the general conception of pH curve. So H. We all know that H is the symbol of magnetic field strength, which is defined as the magnetomotive force per unit length of a magnetic circuit, where the magnetomotive force is provided by a current carrying coil wound around a magnetic circuit. Magnetomotive force is the product of the current flowing through the coil and the number of turns expressed in amperes, though it is generally known as ampere turns. This is the H is the magnetic field strength. The magnetomotive force gives rise to the magnetic flux within the magnetic circuit, the intensity of which is termed flux density, and the symbol is B and expressed in Teslas. So this is known as flux density B. Means when a magnetic force which gives a rise to the magnetic flux within the magnetic circuit, the intensity of which is termed as magnetic flux density, symbol is E expressed in Teslas. The complete pH curve is usually described as a hysteresis loop. The area contained within a hysteresis loop indicates the energy required to perform the demagnetize process. So the pH curve is the complete pH curve is known as hysteresis loop, and the area that contained the hysteresis loop, which is indicates the energy required to perform the magnetize and the demagnetize process. This is the what we have when a pH curve is formed, what we know from it, what we understand from a pH curve. So some terms that is related to the pH curve is magnetic saturation, retentivity, cohesive force, magnetic hysteresis. So first we go for the magnetic saturation. What does it mean? When a magnetization current flows through a coil, the domains of the coil get aligned. This is known to us. When all the domains are aligned, the pH curve reached a constant value and the magnetic circuit is said to be saturated. At this point, any further increase in the field strength has no further effect on the flux density. This is known as magnetic saturation point. Means the increase of the magnetic field strength has no further effect on the flux density. This is generally known as the saturation or the magnetic saturation point. Saturation occurs because the random haphazard arrangement of the molecule structure within the core material changes as the tiny molecular magnets within the material become lined up. You may notice that the flux density increases in proportion to the field state until it reaches a certain value where it cannot increase anymore, becoming almost level and constant as the field state continues or continues to increase. So this is generally known as the saturation. This is because there is a limit to the amount of flux density that can be generalized by the core, as all the domains in the iron are perfectly aligned. When all the domains in an iron are perfectly aligned, it means the flux density, the maximum flux density can be generated. Any further increase will have no effect on the value of M, that is the magnetization, and the point on the graph where the flux density reaches Its limit is called magnetic saturation and also known as saturation of the core at the flux density which is its limit. This is called the magnetic saturation or the saturation of the core. Retentivity, the ability to retain some magnetism in the core after magnetization has stopped is called the retentivity or remanence. While the amount of flux density is still present in the core called residual magnetism. The reason for this is that some of the tiny molecular magnets do not return to a completely random pattern and still point in the direction of the original magnetizing field given them a short of memory means some tiny materials cannot able to return completely and still point in the direction of the original magnetic field. That is why the conception of residual magnetism or the retentivity will come into the play. So retentivity means the ability to retain some magnetism in the core after magnetization has stopped. It's called the retentivity or the remanence. One way to reduce this residual flux density to zero is by reversing the direction of the current flow through the coil, thereby making the value of H, the magnetic field stay negative. By making the magnetic field stay negative, we can uh, reduce the residual flux density to zero. Coercive forces. To reduce the flux density, we need to reverse the current flowing through the coil that we have just learned. The magnetizing force which must be applied to null the residual flux density is called the force. So the force that is required or have to apply to null the residual magnetism or the residual flux density is known as coercive force. It reverses the magnetic field, rearranging the molecular magnets until the core becomes unmagnetized. For materials having low retentivity, that is, soft magnetic materials, coercive force are also low. And for the materials having high retentivity, the hard ferromagnetic materials, coercive force is large. Coercive force is low for the soft ferromagnetic materials and high for the hard ferromagnetic materials. Magnetic hysteresis. The lag or delay of magnetizing due to the magnetization properties of a material by which it firstly becomes magnetized and then demagnetized. It is called the magnetic hysteresis. From the magnetic hysteresis, we will able to understand the conception of magnetic magnetization and the demagnetization. So this is the BH card for the different materials. This is generally seen that this is called the magnetic saturation level, and this is called air and iron and steel, and this is called the magnetic saturation level. So this is the general hysteresis loop. Now, how the hysteresis loop is occurred. So this is the general formation of hysteresis loop. The magnetic hysteresis loop shows the behavior of a ferromagnetic core graphically as the relationship between E and H is nonlinear. It is clearly seen that the behavior is nonlinear. Starting with an unmagnetized core, both B and H will be at 0.0 on the magnetizing curve at that point. At that point, both B and H will be, this is the H portion along the x-axis, and along the y-axis this is the b portion. So at that point 0, O, at that point O, all the B and H are 0. So if the magnetization current, that is I, that is gradually increased uh, in the positive direction to some value, the magnetic field strength H increases linearly. The magnetic field strength, which is now follow the path from O to A, where the magnetization current I increase in a positive direction, that some value of the magnetic field strength H increase linearly with the I, and the flux density B also increase as shown in the curve from point O to point A, and it is heads towards the saturation. So from point O to point A, as the HI increases in the positive direction, magnetizing current, the H and B also increases, and it is shown from point O to point A in this graph. Now at the point A, this heads towards the saturation. Now, if the magnetizing current in the coil is reduced to zero, the magnetic field around the core reduced to zero, but the magnetic flux does not reach zero due to residual magnetism present within the core, and this is shown on the curve from point A to point B. Now, in this direction, point A to point B, in this direction, it is seen that the magnetizing current in the coil that is reduced to zero, magnetizing current in the coil that is reduced to zero, but due to the residual magnetism, uh, due to the residual magnetism present, the magnetic field, the flux, the value of the flux that is does not, at the point of B, the value of the flux doesn't reach to the zero. This is the because of residual magnetism that is present here. To reduce the flux density at point B to 0, we need to reverse the current flowing. Now, to reduce the flux density to 0, we need to, it's clearly seen that we need to reverse the current flowing of the current direction that we have already known. An increase in the reverse current causes the core to be magnetized in the opposite direction, and increasing this magnetization current will cause the core to reach saturation, but in the opposite direction. Point D on the curve, which is symmetrical to point B. Now this point D on the curve, it is clearly seen that point D on the particularly curve where the reverse current causes the core to be magnetized in the opposite direction, and increase in magnetization current will cause the core to reach saturation but in opposite direction. If the magnetic current is reduced again to zero, the residual magnetism in the core will be equal to the previous value but in the reverse point E. So this is the point. This is in the reverse direction. If the magnetic current is reduced again to zero, the residual magnetism present in the core will be equal to, again the magnetic current is reduced to zero, but the residual magnetism is still present within the core but in the reverse direction, and it is uh, given in the point as E. Again, reversing the magnetizing current flowing through the coil, this time into a positive direction, will cause the magnetic flux to reach to zero. Point F on the graph, it is seen that point F on the particular graph where the reversing the magnetic current flowing through the coil, this time into a positive direction, will cause the magnetic flux reach to the zero. Because the magnetic flux reach to the zero. As before, increasing the magnetization current further in the positive direction will cause the current to reach saturation, and the positive direction. This part. Increase in the magnetation current further in a positive direction will cause the core to reach to a saturation point A. So then the pH curve follows the path A, B, C, D, E, F, and A as the magnetizing current flowing through the coil alternates between a positive and the negative values, such as cycle of an AC voltage. This path is called the magnetic stasis loop. A, A, B, C, D, E, F, and again come back to A. This is the hysteresis loop. So use of pH curve. Soft ferromagnetic materials such as iron or silicon steel have very narrow magnetic hysteresis loops, resulting in very small amounts of residual magnetism, making them ideal for use of relays, solenoids, and transformers as they can be easily magnetized and demagnetized. Magnetic hysteresis result in the dissipation of wasted energy in the form of heat, with the energy wasted being in the proportion to the area of magnetic hysteresis loop. Hysteresis losses are always a problem in AC transformers where the current is constantly changing direction and thus the magnetic poles in the core will cause losses because they constantly reverse direction. Rotating coils in DC machines also incur hysteresis losses as they alternate pass from north to south magnetic poles. So, pH curve and the hysteresis loop are valuable tools for comparing the characteristics and behavior of different magnetic materials in order to select them for an appropriate application. So, today we have learned that about the magnetic materials, different type of magnetic materials, their properties and their applications, along with the pH characteristics and the application of pH characteristics and formation of pH curve or the hysteresis loop. Thank you.